Good morning, everyone. Today, we'll be discussing the linear variable differential transformer, also known as an inductive transducer. Let's begin our discussion on a fundamental yet highly sophisticated sensing device in the field of instrumentation, the linear variable differential transformer, universally known as the LVDT. At its core, the LVDT is an inductive transducer specifically engineered for the precise measurement of linear displacement, that is, the straight-line movement or position of an object. To break that down, this device operates on the principle of electromagnetic induction, converting physical displacement into a proportional electrical signal without any physical contact between its moving parts. This non-contact nature is one of its key advantages, eliminating mechanical wear and tear and granting it an exceptionally long operational life and high reliability. The LVDT is renowned for its exceptional accuracy, capable of detecting movements as small as a few micrometers, and its robust repeatability, meaning it can return the exact same reading for the same position over and over again. This combination of precision and durability makes it not just a laboratory instrument, but a workhorse in demanding industrial applications. You will find LVDTs at work in countless critical systems. They are integral to automotive testing for measuring suspension travel and brake pedal position, in aerospace for monitoring flight control surfaces and landing gear, in factory automation for robotic positioning and quality control, and in civil engineering for monitoring structural displacements in dams and bridges. In summary, the LVDT is a premier choice for linear displacement measurement. It marries the elegance of electromagnetic theory with practical, rugged design, offering a blend of non-contact operation, high precision, and outstanding reliability that few other sensors can match. It is a perfect example of how a well-understood physical principle can be engineered into a vital component for modern technology. With that foundational introduction, we will now delve deeper into its construction, operating principle, and characteristics. Now that we understand what an LVDT is, let's explore why it is so widely preferred over other types of displacement sensors. These reasons highlight its distinct advantages in both precision and durability. First and foremost, the LVDT is chosen for its exceptionally high measurement accuracy. It can reliably detect and measure movements as small as millionths of a meter, providing a stable, linear output that is directly proportional to displacement. This makes it ideal for applications where precision is non-negotiable. A key feature contributing to this precision is its completely frictionless operation. Because the moving core does not make physical contact with the coils, there is no mechanical wear. This eliminates a major source of error, hysteresis, and long-term degradation found in contact-based sensors like potentiometers. This lack of physical contact directly leads to another major benefit: an extremely long operational life. With no parts rubbing together, an LVDT can often last for decades without performance loss, significantly reducing maintenance costs and downtime. Furthermore, the LVDT provides a very stable and reliable output signal. It is relatively immune to variations in temperature, humidity, and even minor electrical noise once properly conditioned. Its output does not drift over time, ensuring consistent readings. Finally, its robust construction, often featuring stainless steel housings and sealed units, makes it highly suitable for harsh environments. LVDTs can operate reliably in the presence of dirt, moisture, extreme temperatures, and high vibration, which are common in industrial, aerospace, and automotive settings. In summary, the combination of high accuracy, frictionless design, longevity, signal stability, and environmental robustness makes the LVDT the sensor of choice for critical displacement measurements across a vast range of demanding industries. Let's now examine the basic construction of an LVDT, which is elegantly simple yet ingeniously effective. At its heart, the LVDT consists of three essential components. First, we have a set of coils. There is one primary coil, labeled P here, located at the center. On either side of it, wound symmetrically, are two identical secondary coils, labeled S1 and S2. These three coils are wound on a common, non-magnetic cylindrical former, ensuring precise alignment. The second key component is the movable soft iron core. This is a rod made of a high permeability ferromagnetic material. It is attached to the object whose displacement we want to measure, allowing it to slide freely along the axis inside the coil assembly. This core is the heart of the motion detection. Finally, we have the electrical connections. An AC excitation voltage is applied to the primary coil P. This creates an alternating magnetic field. The two secondary coils S1 and S2 are connected in series opposition, meaning their voltages oppose each other. The final AC output voltage we measure is the difference between the voltages induced in S1 and S2. In summary, the construction is a symmetrical arrangement of one primary and two secondary coils, with a movable ferromagnetic core passing through them. The position of this core modulates the magnetic coupling between the coils, which in turn creates the differential output signal that tells us both the magnitude and direction of displacement. Now, let's delve into the principle of operation that makes the LVDT work. It's a brilliant application of fundamental electromagnetic theory. The process begins when an AC supply is connected to the primary coil. As this alternating current flows, it creates a continuously changing magnetic field around the coil. According to Faraday's law of induction, this changing magnetic field will induce a voltage, or an electromotive force, EMF, in any nearby conductor. In the LVDT, the two secondary coils, S1 and S2, are positioned within this magnetic field. Let's denote the voltage induced in the first secondary coil as E1 and the voltage induced in the second as E2. Here is the critical design feature. These two secondary coils are wound in series opposition. This means their induced voltages are 180 degrees out of phase. When one is positive, the other is negative. Therefore, the net output EMF we measure from the device is not the sum, but the difference between these two voltages. Net EMF equals E1 E2. This differential output is the key. When the movable core is perfectly centered, the magnetic linkage to both secondary coils is equal. Thus, E1 equals E2, and the net output is 0. This is the null position. When the core moves, it changes the magnetic coupling asymmetrically, making one voltage greater than the other. The magnitude of E1 E2 tells us how far the core has moved, and the phase of this net voltage, whether it is in phase or out of phase with the primary supply, tells us the direction of movement. In essence, the LVDT cleverly uses a differential transformer principle to convert a physical position into a precise, directional electrical signal. Let's examine the first and most fundamental case of LVDT operation, when the movable core is perfectly centered. This is the starting reference point, known as the null position. When the core is centered, it sits symmetrically between the two secondary coils, S1 and S2. As a result, the magnetic flux from the primary coil links equally to both secondary windings. Because the coils are identical and the magnetic coupling is balanced, the voltages induced in each coil, E1 in S1 and E2 in S2, are equal in magnitude. However, due to the critical design feature we discussed, the coils being wound in series opposition, these two equal voltages are 180 degrees out of phase. This means they have opposite polarities. When we take the differential output, E equals E1 E2, the two equal but opposite signals completely cancel each other out. Therefore, at the null position, the output voltage E is 0. This zero output state is highly significant. It provides a clear, stable electrical reference point that corresponds to a known physical center. Any movement away from this center will break the symmetry and produce a measurable voltage, allowing us to detect both the magnitude and direction of displacement from this precise null point. Now, let's consider the second case, when the core moves to the left-hand side. Imagine the movable iron core is displaced to the left. As it does, it moves closer to secondary coil S1 and farther from secondary coil S2. This physical shift has a direct magnetic consequence. The core, being highly permeable, channels the magnetic flux from the primary coil. Because the core is now nearer to S1, a greater amount of magnetic flux links with coil S1 compared to coil S2. According to Faraday's law, a greater flux linkage results in a higher induced voltage. Consequently, the induced EMF in S1, E1, becomes significantly larger than the induced EMF in S2, E2. Now, let's calculate our differential output. E equals E1 E2. Since E1 is greater than E2, their difference, E, is a positive value that is greater than 0. This positive output voltage has a dual meaning. Its magnitude tells us how far the core has moved to the left. Its phase, which is in phase with the primary excitation voltage, confirms the direction of movement is to the left. In summary, a leftward displacement breaks the magnetic symmetry, favoring S1, and produces a positive differential voltage proportional to the distance moved. Advantages and disadvantages. Advantages. High accuracy and good repeatability, provides precise and consistent measurements. Suitable for harsh environments, can operate reliably in conditions with dust, oil, and vibration. Non-contact measurement, no physical wear, leading to minimal maintenance. Good linearity over a limited range, output is proportional to displacement within its designed range. Long operating life and reliable, durable with a long lifespan under proper conditions. Disadvantages. Can detect only metallic objects, requires a ferromagnetic or conductive core. Output affected by external magnetic fields, susceptible to electromagnetic interference. Bulky compared to capacitive sensors, larger size may limit use in compact applications. Requires AC excitation and signal conditioning, needs additional circuitry for power and signal processing. Limited frequency response, not ideal for very high-speed dynamic measurements. Applications of LVDT. Displacement and position measurement, primary use in precision engineering and testing. Proximity detection of metal objects, in automation and safety systems. Thickness measurement of metal sheets, in rolling mills and quality control. Speed and vibration measurement, for condition monitoring and dynamic analysis. Industrial automation and machine tools, for precise tool positioning and feedback. Valve position sensing, in process control, hydraulics, and pneumatics. In conclusion, inductive transducers, and the LVDT as a prime example, are highly reliable and accurate sensing devices. They operate on the fundamental principle of electromagnetic induction to measure key physical quantities like displacement, position, and proximity. Their design makes them especially well suited for industrial environments, thanks to their non-contact operation, robustness, and long service life. While they do have limitations, such as detecting only metallic objects and requiring AC excitation along with signal conditioning, their high accuracy, excellent repeatability, and ability to perform reliably in harsh conditions make them indispensable in many fields. You'll find them at the heart of applications like LVDTs, machine tools, and automated systems, where precision and durability are non-negotiable. Overall, inductive transducers remain a highly effective and trusted choice for precise, long-term measurement across a wide range of engineering and industrial applications. In short, inductive transducers like the LVDT are reliable, accurate sensors that work without touching the object they measure. This makes them tough, long-lasting, and perfect for industrial use. They are great for measuring position, movement, and proximity, especially in machines, factories, and automation systems. Thank you for your attention. That concludes our presentation.